Today, I'll show you how to master this tool's parameters to optimize your modeling workflow. Let's get started. This clip is dedicated to introducing the group node asset. I've already made a video covering the tool version, you can find the link below. First, drag and drop this group node directly from the asset browser. By default, it operates exactly like the Voronoi face splitter tool. Notice the high icon in the top right corner of the node, it's reporting the output as 19 mesh islands detected. This information is also displayed in the modifier panel, making it easy to monitor our data flow. Compared to the default tool, this group node has two key differences. First, I've added a Voronoi seeds panel with a drop-down menu, and grouped weld vertices cleanly inside output control. Second is the instance output feature. When you check this box, the system instantly converts the mesh islands into instances. This is absolutely crucial for memory optimization workflows. You can check the icon in the top right again, the output diagnostic has automatically updated to 19 instances detected. To keep it short and easy to visualize, the random and Poisson disk options in the Voronoi seeds panel work exactly like the default distribute points on faces node. Look at the parameters and you'll see the similarity. Distance min, density max, and cell density here is essentially the density factor. Just apply your familiar point scattering logic to control this group node. Basically, this group node will fracture any face that passes through it. For example, with this cube, the output returns surfaces fractured into Voronoi patterns. However, I have an important optimization warning. With highly detailed models, absolutely do not throw all your data into this, use a separate geometry node to isolate and input only the faces you actually need to cut. Look at the timing indicator on the node, it's costing us 10 milliseconds. Forcing the system to calculate unnecessary surfaces will drain resources extremely fast and lag your viewport. Next, we switch the menu in Voronoi seeds to custom mode. The node will now expand to reveal a manual point input socket and a more precision for custom toggle. You must pay strict attention to the data flow here, the input data must be points. The system will not work if you plug vertices directly into it. For instance, if you use a mesh circle, remember to pass it through a mesh to points node first. Furthermore, when the system calculates Voronoi based on perfectly distributed points, like from a regular polygon, the algorithm is prone to mathematical precision errors. Checking the more precision for custom box will fix this. However, you might still see some minor glitches appearing on the mesh occasionally. That's a technical limitation of the tool that we just have to accept. Instead of talking pure theory, let's jump straight into a practical application, using this group node to create a fractured Voronoi terrain that interacts directly with a Bezier curve. As you can see, the curve will now act as a controller to shape the fracture structure. First, we bring a Bezier curve into the workspace. From the original geometry, connect the wire straight into the distribute points on faces node. To allow the curve to interact inside geometry nodes, we need an object info node pointing directly to it. Pay special attention here, do not forget to check the relative box so the system grabs the correct original coordinates. Next, we use a geometry proximity node to calculate the interaction distance, setting the target to edges. However, since this node only works with mesh structures, we must convert the curve data using a curve to mesh node before plugging it in. At the scatter node, switch to Poisson disk mode and crank up the density max. Now let's handle the math. We need to normalize the distance value from the proximity node using a map range node. Simultaneously, from that same distance socket, pull a wire straight into the field min-max node. Just observe and match the wiring exactly as shown on the screen. If you check the output values right now, you'll see they don't align with the shape of the input curve at all. To fix this and see the interaction clearly, we'll go back and insert a subdivide mesh node between the original geometry and the scatter node. As you increase the subdivision level, look at the viewport, you'll see the calculated values start to closely follow the input curve. Next, we need to invert the map range values, set to min to 1 and to max to 0. When we plug this output into the density factor, we force the system to understand, the closer to the curve, the more points it scatters. Pass this through an additional float curve node to aggressively boost the contrast of the black and white mask you're seeing. At this point, the Voronoi grid has formed, but notice the calculation timing is getting quite heavy. To optimize the workflow, we will immediately insert a bake node here to freeze the data, directly reducing the load on your machine. For the final step, use an extrude mesh node to push the faces up, and repurpose the output data from that previous float curve to drive the shape. If you want to independently adjust the height for this extrusion, simply insert another float curve node into the data flow, and you're done. Thank you for checking out my work. I would truly appreciate your support if you decide to purchase this product. It helps provide the resources I need to keep developing even better tools for us. Happy working!